say he has failed. He needed more time, so he did not finish what was his the dream research. Okay, so yeah, as such, we can still use the required basic physics laws wherever we are studying. When we are studying at quantum level, we have to use the quantum physics laws. And classical case, we have to use classical physics laws. Astronomical case, astronomical laws. Especially in the black holes, why the basic physics laws we are saying right now may not work because the amount of gravity is humongous, right? So the gravity is so much, there is nothing, you cannot have a chance to do some experiment there and find out whether the laws are applicable there or not, right? So that is what the black hole, you can't go near to it. The moment you, if something goes near to it, is sucked in. So what is happening, nobody knows inside of it, right? Okay, so right, so without
Yeah, we can
wasting
start, sir. We can.
further
We can.
time, yeah. So yesterday somebody was asked me a question. I think Dr. Padmavati ji, I think. So if you can give me some sensors, quantum sensors, then we will understand what is quantum sensing. That's what the question was asked. Please remember, so there is a full-fledged course on quantum sensing. Okay, this is QT-07. Here you see, starting from very basic physics and basic even understanding light, which is going to be used as a sensor. Okay, so those things were actually covered in that entire uh, quantum sensing QT module. Okay, so if to answer a specific question, what you asked, here you see there is atom state based sensing. So atom based sensors are there. There is solid state based spin based sensors are there. These are all like they will have a probes where atoms are concentrated. Those atoms will be used to do the probing. Okay, right? So just a minute. Yeah, fine. I think we can start. Uh, Yesterday, what we were doing. Let me quickly use my drive. Okay, 1 minute. Yeah, right. So we were doing yesterday. Just a minute. QT-00. Yeah, which this lecture. Yes. So we started with, I think a lot of text is there, but don't worry. We started with understanding what is a qubit being used for sensing. Okay, so in sensing we have to use some kind of a probe, a tool. A qubit can be a tool for us. So the two qubit if I use, okay, and how it undergoes a change, depending on the change we are going to measure the environment effect or some signal effect on the qubit. So straightforward, the qubit gets affected through its probability amplitude alpha and beta. So depending on alpha and beta, okay, we can notice how much change it has undergone. Okay, right? So, okay, is there any highlighter? Yeah, it is not there. Okay, fine. Anyway, we have seen this. And then the amount of change or kind of a change it has undergone is represented in terms of unitary operator. So unitary change U from T0 to T1 it has gone on change. Okay. So in fact, U consisting of the Hamiltonian of the system. Hamiltonian in the sense it is a matrix which captures the information of the system. For this case, it is a qubit and its surrounding. Okay, right? So a simple Hamiltonian we just saw, right? For example, if it undergoes a change, how do I connect that change? Okay, right? Yeah. How does it undergo a change? We can show it here through some transformation matrix here. In fact, this transformation matrix is a unitary operator. We have showed here as a proof. Okay, right? Now, if you see, let's say a energy operator, like we are going to write the equation of eigenvalue, which tells me how a quantum system or a quantum states, different quantum states exist because system undergoing change from one state to other because of this environment around. So that is actually expressed in terms of simple mathematical equation called eigenvalue equation, which is h psi is equal to e psi. So we are talking in terms of quantum physics or quantum mechanics, where every operator undergoes change or like some kind of a representation of operator. So E is represented as a time derivative operator. So the moment E I represent as IH cross dou by dou t, so the probability amplitudes also get operated or get operation from the time derivatives. Okay. On the left side, on the right, I have a Hamiltonian, and here I'm only writing the Hamiltonian of the system itself. I am not writing the Hamiltonian of the environment. Okay. So if I do that and I will have a two differential equations, I can solve the differential equation by interchanging the like terms onto one side. Okay. And then integrate it, and what you get is alpha and beta time dependent alpha betas are actually related to the old alphas, alpha naught and beta naught, and where the connection is through some exponential expressions. Okay, so by looking at this final equation, I can write that into a matrix multiplication, where the matrix whatever is given here is actually unitary operator, which is created out of the required Hamiltonian. So exponential minus I Hamiltonian multiplied by t by h cross is the unitary operator for us. Okay. And there is another way also we could see this effect of environment or the change of a quantum system. In this case, particularly the quantum qubit undergoing a change, I can see from other aspect also. What is that? Again, let's say if I put unitary operator u changes the quantum system from psi of 0 to psi of t. Okay, right? So there is a time dependent Schrodinger equation I can write down. So which is actually a eigenvalue equation. Okay. So here, okay, let's replace psi of t with the unitary multiplying onto psi of 0. And when I put it on the right hand side, left hand side, if I compare, if you see, there is a psi of naught and psi of naught is ket form, it is there. So I can just ignore the ket form just like a cancellation and write down the derivative of the unitary operator is just equal to Hamiltonian multiplying onto unitary operator. Okay, again, if you do rearrangement, okay, bring u to the left, okay, dot t to the right and integrate, okay, and what you get is a ln of, or the natural logarithm of u of t is equal to minus I by h cross Hamiltonian multiplied by time. Okay, right? On the right hand side, integration of dou t is just simply t. Okay, right? So the log of u is minus I by h cross h Hamiltonian into t. And what would be the u? U is simply, if you send the logarithm to the right, it will become exponential function. Okay, right? So now T is U is actually relating a system from zero time to some T period. Na? So if I have instead of saying zero time, let's say specific some T naught to T, if I have to connect the quantum systems, okay, in time and how it is progressing or evolving, I simply replace T with a T minus T naught. Okay, right? So this is how the unitary operator helped me to connect the quantum system being undergoing some change. Okay, now we use that mathematics, this important, this mathematics of finding a right unitary operator to represent a change in the system. Okay, we use that and we'll go ahead and understand what is quantum sensing is all about. Okay, so quantum sensing is nothing but using a quantum system and their quantum properties which undergo some change due to some interaction with the environment. How much change it undergone, we will measure it, and that is what we are going to say it as the sensed information. Okay, right? In fact, this quantum sensors are so fragile and sensitive, we will get more precision and sensitivity in the calculation or measurements. Okay, so there are historical examples. Okay, so the one which is semiconductor quantum interference devices were used back then, and even atomic vapors and atomic clocks were even used before the invention of computers and quantum computers. Okay, right? So which are actually based on magnetometers base, means something to do with the magnetic field variation. Okay, when external field is acted on some magnetical material which are sensitive to the external field. Okay, right? So recently quantum sensing rapidly growing branch of research which is under the umbrella of quantum science and technology. So, in NQM, IIT Bombay has got a quantum sensing hub. They are working on NV center based quantum sensing devices, and there are sub teams like IIT Bhopal, sorry, ISR Bhopal and IIT Kanpur. They are working in a like another couple of domains. For example, IIT Kanpur is working on entangle enhanced quantum sensing effect. Okay, ISR Bhopal is actually working on using quantum sensing for magnetic field detection and other things. Okay, and especially IIT Bombay is working on sensing quantum sensing for biomedical applications. Okay, right? So the most common platforms being used for quantum sensing are spin qubits, trapped ion qubits, and flux qubits. We have seen what is spin qubits means. The magnetic spin of a nuclei or an electron is used as a tool. Okay, right? It's used as a tool to measure the external field effect. Okay, so Venkat Reddy ji is asking, please share the notes. I have already shared on the Canva. Okay, so please check under my name. This is there already. Okay, now the trapped ions means we will use the ions trapped between the electrodes, and from there we can use we can create a quantum qubits. Those qubits are going to be very sensitive to the external field, so that here that the electrodes which we being used are merely using like purely they were used for holding ions. They are nothing to do with the inducing change in the ions, just to hold the ions. These electrodes were used. Then using these electrodes, the ions can be carried to the testing location. Okay, right? So testing location, and then we will test. Okay, fine. And right, and one more thing. Fine. 1 minute. Right. Okay. So yeah. So there is the abundance. There is a flux qubits. Flux qubits are like they are like a magnetic field induced current qubits. Okay. So if I use a loop of superconducting material, not only just superconducting cable, between I'll have a resistance junction. If I have something like this, it is going to create a current in clock or anti-clockwise in the clock or anti-clockwise in the states of quantum qubits. Okay, either 0 qubit and 1 qubit correspond to the clock and anti-clockwise current direction. So in that way, we can realize the qubits out of it, and these qubits are very very sensitive to the external field. The moment the external field is there, these probability amplitudes of this clock and anti-clockwise current direction are going to be disturbed. How much disturbance is created, depending on that we can sense the external fields. Okay, and we can exploit this central weakness of the quantum systems. I mean, this fragility and sensitivity of quantum qubits we can use to do a sensing. Okay, right? So here I am saying quantum systems are known for fragility or vulnerability towards external disturbances or environmental interactions. So even before the birth of computers, the above nature of quantum system is being used to realize a sensing effect. Okay, like we yesterday discussed, the light meters were being used earlier. Okay, now quantum sensors would allow us to measure magnetic fields and the electric fields. Okay, so even for high resolution spectroscopy, the quantum sensor is being used. Okay, so a single atoms are actually being investigated for sensing, where entanglement could be added to even enhance the sensing to a greater extent. Okay, right? So what does quantum sensing describes in a nutshell? We have discussed there are three ways we can realize the sensors, right? So whether classical or quantum, there is a one way of measuring the sensing effect by taking a particular kinds of quantum qubits. Okay, so that is all we discuss. And then, so just for a quantum qubit to become a quantum sensor, there are some criteria to be satisfied. Number one is we should have us that qubit to have a discrete states, and we should be able to initialize to a known states. Uh, class. I'm in a class. Okay. So it should allow coherently manipulation. Okay, that means it should coherently interact with the environment, and the system should allow us to measure, okay, whatever external changes it is undergoing. Those things we should be able to do. Okay, we discussed that in detail yesterday. Okay, so the types of quantum sensor, the how we can classify the sensors is simply based on how they are used, for what purpose they are used. So one is we can use electric field sensing, another one is magnetic field sensing. So there are the two basic types. For the charge sensing or electric field sensing, we use the charge sensors. For magnetic field, we use the spin-based sensors. Okay, right? So in general, sensitivity is inversely proportional to the coupling parameter and also inversely proportional to the decoherence time. The sensor goes out of control or out of coherence, that is called decoherence in certain time. So we have to sense the external signal within that time. So where decoherence time is mentioned as d chi. Okay, right? So we need to balance the system so that we can sense the external signal. Okay, when it comes to methodology, it has three steps: initialization, interaction, and readout of the sensor. Okay, right? So yeah, there is one example we discussed yesterday. Now we went on to discuss the mathematical description of the quantum sensor. Okay, so the mathematical description As we know, quantum sensor is undergoing unitary transformation. Unitary transformation consisting of a Hamiltonian of the entire system plus the environment. So here the Hamiltonian we have to mathematically write, which is appearing like H naught plus HV plus H control, where H naught is purely system, the qubit, for example. In our case, is a single qubit Hamiltonian. Okay, and for signal Hamiltonian, there may be two components coming in, two parts are coming in. One is the parallel part, another one is perpendicular part. So basically what they are is, so the parallel part induce some change in the qubit in one way, perpendicular part will induce the change in qubit one another way. So that's why we need to separate the in signal Hamiltonian accordingly. So the parallel component we can have in the form of half, where gamma is a coupling parameter, V per parallel, there's a constant, and it is going to be having terms of what is given on the left hand side. That is what the Hamiltonian is. Okay, and V parallel would only multiply to the diagonal terms only. Okay, right? So V perpendicular on the other case would multiply to off diagonal terms. Okay, so here there is something called a Zeeman shift, means the given orbits are the atomic levels get split into the multiple levels. Here in this case I showed into two levels. The splitting can happen due to magnetic field, or it can even happen due to electric field. So if it happens because of magnetic field, it is called Zeeman shift. If it happens due to electric field, it causes Stark shift. Okay, so basically both the electric and magnetic field will induce a change in the orbits of the system or the electron. Okay, right? So if somebody has any questions, please pose it now, we'll discuss. Okay, so what is the effect of the parallel component of the signal? If you see, so because of the parallel component, what happens, the levels get split. So existing energy separation of two orbits is going to be either expand or reduce by energy gap. So that is what the parallel component would affect. When it comes to perpendicular component, perpendicular component would induce the rate of like a rate of decay of electrons from excited to ground. It's like, say, if an electron is excited to the excited state for a 1 microsecond time, even before that, the electron gets decaying because of this perpendicular component effect. So we need to have a measuring or a sensing to be done within that time. And remember, we need to induce the sensing effect in resonance with the transition. In that way, we can have a better sensing effect. Okay, so the incoming energy of the signal must be exactly equal to the energy gap between 0 and 1. How do we do? We can just shift the energy levels of this system according to that. Okay, or we can choose the required probe which matches with the incoming signal strength. Okay, right? So I think this part we have not discussed. I think we will start from at this moment. Okay, let me use my hand notes. Okay, right. Yeah, fine. Okay, yeah, there's some mathematics is there. I think you have to bear with me, please. Okay, so the Hamiltonian. Okay, it's too much thickness wise. Let me reduce. Okay, so the Hamiltonian is, okay, Hamiltonian consisting of what? the qubit Hamiltonian plus signal Hamiltonian plus control Hamiltonian. Okay. Why we need to go for Hamiltonian? As we know, the quantum system, the new state is actually connected by the old state by unitary operator. So where the unitary operator is in fact exponential I h t by h cross. Okay. So to know how much change the system has undergone, okay, to know how much a sensor has undergone a change, okay, we need to, okay, we need to know the u, okay, and to know u, okay, let me write down a second point, okay, right? So, okay, to know u, okay, we need information, okay, we need information on h, okay, we need to know even h. The moment you know h, you can calculate u. The moment you know u, you can calculate what is psi. Okay, it's all interconnected. Fine. So now there are few things I have to ensure if people are knowing it. So every time we write quantum qubit as 0 and 1. Okay, what are these 0 and 1? When I say a qubit is having an electron in the ground, okay, so quantum state is like this. Okay, what is this is? It is a short version of writing. Let's say there is a, if there is an atom, there is a nucleus, there are orbits, okay, like that. Orbits are there. I'm just exaggerating. Orbits are not of equal distance. As you go further and further, orbits comes very close. Okay. So let's say this is a ground state. Okay, ground state, which is very close to the nucleus. So it is, let's say, ground state electron as orbit. And let's say this is the next one is excited state. If I just take a snapshot of that reason, or you can write that as 0 and 1 as a quantum orbital states or orbit states of the electron. Okay, right? So now, fine. So sometimes because of the external effect, alpha and beta undergo change. Okay, so that change we will use to recognize how much effect is there from the outside world. Okay, right? So now I was telling you all earlier the HV parallel. Okay, so HV what we have? Okay, HV parallel is actually going to have an effect on the individual orbits. If there is a ground state orbit, that orbit is going to split into two or many sometimes. Even the excited state going to split into two or more. Okay. So let's say this induced existing energy separation is H omega naught. Okay, after splitting, if the electron is happen to be in this state, so the splitting, after splitting, if you see energy separation is much smaller. Okay, so we can say which is not equal to h omega naught. Okay, so this is the effect caused by parallel parallel component. Okay, right, basically the parallel component going to induce a change in the separation of the orbits. Okay, and when it comes to perpendicular component, okay, what it does is it is going, say there's an electron in the excited state is there. If it is gone after taking some absorption of a photon, it's supposed to exist there 1 microsecond. Even reaching 1 microsecond, what it is decays with some decay rate of 1 over T1. Okay, so because of this, what happens? Okay, this is actually caused by environment, right? Induced decay. Decay is induced by this component. Okay, because of this, I need to work fast because the system is not going to behave as per my wish. So where H naught is supposed to be, okay, equal to H into frequency of the signal. Okay, right? So I have to very fast, I have to work so that system would behave without any decoherence. Now this is the physical implication or physical description of perpendicular and parallel components, right? Okay. Now, what is a mathematical form? If you ask, a mathematical form would be HV. Okay, HV of t, it's a time dependent, is usually equal to the coupling parameter multiplied by some vector field dot product with the polyvector. Okay, this is the mathematical expression. Now, what did I write here? As we know, okay, the signal is consisting of, okay, consisting of electric fields and magnetic fields. Okay, so which means there is electric field and magnetic field involved. So we will use V of t, a vector field to represent, okay, these electric field and magnetic fields. Okay, so what I mean is the V of t would be having a component along x direction, a component along j direction, a component along z direction or k direction. Okay, right? And here I have written a Pauli vector. Okay, Pauli vector sigma is actually sigma xi plus sigma yj plus sigma zk. Okay, so that is what the Pauli vector is. Pauli matrix, as you guys know, sigma x is a x of matrix, sigma y is a y matrix, sigma z is z matrix. Okay, right? Now, if I just to take HV, the substitutes V and sigma in the HV not expression, HV expression, what I'll get? I'll be getting, okay, Vx, let me write sigma, gamma, gamma, okay, what I'll have? Vx sigma x, Vy sigma y plus Vz sigma z. That's all. Very simple. Okay. Now, if you see among them, what are the components which are along the parallel imposition or the parallel effect? What are the components which gives a perpendicular effect? So let me tell you, this Vz is actually, okay. Vz is actually a parallel component. Okay, and Vx plus I Vy is a perpendicular component. Okay, so Vx and Vy together becomes a perpendicular components. Okay, right? So I can also write in terms of, since the perpendicular component is a complex number, what we can be, if somebody doesn't bear with the complex iota, they can simply write gamma into the real part of V perpendicular into sigma x plus imaginary part of V perpendicular sigma y plus V parallel sigma z. Okay. So here I'll put a hat for sigma to represent they are in the operator form or in the form of matrices. Okay. Right. So even V can also become a operator explicitly when I get to know what is the V perpendicular component and V parallel components. Okay. Okay. So the V parallel means the signal is a part of the signal, I should say. A part of the signal, or the signal, not a part. The signal is, okay, signal is having a component. V means signal component in the direction of qubit alignment. Okay. Now I say qubit alignment means it's like a dipole moment. Qubit is going back and forth, some kind of oscillation it creates. So that is the incident signal is exactly in the oscillating in the same, or polarization it is in the same direction. Okay, right? Now coming back to the next part of the Hamiltonian, which is control Hamiltonian. Okay, so the third part of the Hamiltonian is control Hamiltonian. Okay, what is the use of this? The use of this is to control the sensor not to interact too much, not to interact very little. Like appropriately, it should interact with the signal. That much we can have through this control Hamiltonian. Okay. So for sensing process, what is required is we need to manipulate. For example, here in our case, we need to manipulate the qubits. Okay, so either before or after sensing the process. Okay, we need to do both in the both the case sometimes, but literally while preparing, we need to ensure it is not going to interact with any noise. So, right? Uh, yeah, yes. So somebody was saying repeat. Okay, that is earlier. Okay, I hope I have repeated. Now, the control to achieve is achieving control is done by a simple quantum gates. Okay, so control is achieved by a simple quantum gates. Okay, what kind of a quantum gates we can use to control the system? As we know, number one, Hadamard gate. Okay, and number two is the Pauli X sigma X gate, sigma Y gate, sigma Z gate. Because literally they are X gate, Y gate, and Z gates. And also we can use the quantum gates are nothing but the rotation gates, right? So we can use some set of pi by 2 and pi rotational gates. You see, these gates are rotation about some axis, right? So which means I can have the rotation about x-axis by pi by 2 or rotation about x-axis by pi angle. Similarly, rotation about y-axis by pi by 2 or rotation about y-axis by pi, right? So there are so many other gates we can think in this way just by varying the angle or by varying the direction about which we are going to rotate. So in this way, we can have a control on the system. Basically, this control gates are actually achieved through by sending a pulse of photons. Okay, right? So through the pulses of photon, these control gate operations are realized. Okay. By the way, how they are realized? As you can recollect, okay, so block sphere is being introduced to people. So what is a block sphere? There is a I cap, there is a j cap, there is a k cap. Three-dimensional Cartesian coordinate system. I can have a sphere. Okay, there is a equatorial plane. Okay, let's say there is a quantum state psi, which makes an angle theta with x-axis. And if you just drop a vector on the onto the equatorial, so it will going to make a shadow. That shadow creates an angle phi. Okay, this is the shadow. Okay, now if you see, if the vector is pointing along the k direction, which is equivalent to having a quantum state in 0. If the vector is pointing along the minus k direction, in that case vector is going to, the quantum state is going to be 1 kT. Okay, so now if I use the x gate on 0 kit, it becomes 1 kit, so which is like rotating about the x-axis with 180 degrees. So the x operation is equivalent to, or x gate operation is equivalent to rotate the quantum state psi about x-axis, you can say unit vector I, okay, about x-axis with an angle or a radian, okay, of pi 5 degrees radian. You are rotating from top to bottom, north pole to south pole. That is the x gate operation. Okay, if you do rotation about pi by 2 degrees, again let's say I will do about the x-axis, so rotation about the x-axis pi by 2 on the quantum state 0 would is going to give me what? It is going to give me 0 plus I1 divided by 2, which is actually written as I ket, which is along, this is along y j cap direction. So it will be pointing in this direction. If you rotate about the x-axis 0 ket from north pole to the equatorial plane, right hand side, it is okay. So here you see, okay, there is a rotation gate like that. And also I can rotate in such a way, okay, if I rotate about the y-axis, a pi by 2 rotation, if I do on 0 cat, what it gives me? It is going to give me 0 plus 1 divided by square root of 2. What is this? This is a just plus cat. Okay, this is the plus cat, which is along I cap direction, x direction. Okay, so basically what I'm doing, I'm rotating about y-axis and bring the 0 ket from north to equatorial plane onto the x-axis. That is the rotation about the pi by 2. Okay, and if there is a rotation, if the vector is along quantum state is along the plus direction. Okay, then what I do, if I rotate about z axis about pi by 2 on the plus gate, what I am going to get? I am going to get, okay, in a clockwise direction, so anti-clockwise direction I'm talking about. So if I rotate from I to j, which would be the rotation about z axis with a pi by 2. So what I'll get? I'll get plus I cat. So in short, we'll write I cat. So what is that? Which is this. So what you see here is the gates are rotations about some axis with some angle. Okay, whether you take x gate, y gate, or z gate, or we take rx, ry, and rz. Okay, there is one more gate which we have not mentioned here, the z gate as it is. What is that? 1 0 minus 1. Okay, so what is this gate? Is in fact it's actually phase gate 1 0 0 exponential I pi. This is actually inducing a pace of pi onto the system, which is, if we act z on 1, okay, what I'll get? I have 1 0 0 exponential I pi 0 ket 1 ket. Okay, this is 1 into 0 multiplied 0 and 1 is 0, and 0 exponential I pi, I'll get exponential I pi, which is my exponential I pi into 0 1. What is exponential I pi? Exponential I pi is cos pi, okay, plus I into sin pi. So I in sin pi is 0, so cos pi is minus 1. I will get, what I'll get? I'll get minus of 1 ket. So Z gate is actually inducing a phase of exponential I pi. It's a pi radians it is inducing onto quantum 1 ket state. Z is not going to induce any change to 0 ket. It is only a induce a change to 1 ket. Why? Because you can just see mathematics 0 exponential I pi 1 0, which is going to give me only 1 0. So there is no change. Okay, right? So what people do is they use, okay, they use x gate, y gate, z gate, okay, all right, and rotation x gate, rotation y gate, rotation z gate, even the Hadamard gate to control the quantum sensor. Okay, let's say I have a quantum sensor which is having multiple qubits. Okay, if the quantum sensor, if the quantum sensor have multiple qubits, in that case, okay, then we might need to use, we may need to use the control control inducing qubits like control not or control unitary gates. Okay, what are those gates? You know already, which is, there is a control, there is a target. This is a C naught gate, and there is a control, there is a unitary operator acting on the target. So this is a CU gate, controlled unitary gate. Okay, or you can say in short, controlled phase gate. Okay, they're all phase inducing gates, right? Okay, so the control Hamiltonian systematically tunes the quantum qubit sensor to have a transition h naught h omega such a way that it meets the risk, like meets the possibility of having interaction with the environment. Otherwise, if it is not meets the environment in sync, will not be able to measure it. Okay, it is simply like if you have So it is simply like if you have a thermometer, if you want to measure some person's temperature, what you should do, you should bring close to him. You can't stay keep it away and expect the temperature to be measured. Okay, right? Now, let's try to understand the quantum sensing protocols. Okay, quantum sensing protocols we'll try to understand. As you know, the quantum sensing protocol involves three steps: quantum sensing protocols. Okay, so it involves step one, initialization of the quantum sensor to known states. Okay, and then what we do, we are going to let the quantum sensor to interact with the environment. Okay, right? So initialization and then into the known states. That is there are two processes involved in the first step. In the second step, we'll let the system to interact with the environment. Okay, interact with the signal. Okay, and the third step is, okay, then we will measure the effect. Okay, we will measure what is the change in the state. Okay, from psi of 0. Okay, right? So the first step is what we'll do. First, we'll prepare the system in 0 state. Means as if the atom in the strictly ground state. Its ideal situation. It's ideal situation. So the quantum state I am starting with electron in the ground state. Okay. And next, what I will do is then I will prepare the system into the known superposition state. So the known superposition state is I will use the unitary matrix consisting of I H naught, remember, T by H cross, where H naught is simply E naught 0 E1. Okay. So if I do this, what happens? The quantum state in superposition is prepared. Okay. So now I can say the electron is not just confined to ground. It is actually hopping between ground and excited. So it is in superposition. Okay. So initially may not be in superposition. Even if it is in superposition, it is not in our control. It is going as per its wish. Okay. So this like first step is done. Now the second step is interaction with the environment. So as you know, the moment interaction, the signal comes, the Hamiltonian gets added up by the signal Hamiltonian. At that time, we want to have a control on the system. So I'll add some control signal. So overall Hamiltonian would be this one. Okay. So now the interaction with the environment or signal is represented as what? New quantum state forming with the unitary operator acting on the old quantum known state. Okay. So if you want, you can specifically write down, okay, unitary operator from time 0 to time t. It is pushing the system from 0 to time t. Okay, right? So now remember one thing, the new quantum state which is formed may not be ideal situation. Means what I mean is, let's say I just take a collection of qubits, all are alike. Okay. So initially all of them are alike. So I represent all of them by quantum state psi 0. Once some signal is incident, signal coming in, which is going to induce some change in the system. Remember, not all atoms undergo so induce some change. Only the one which are in the interaction zone only undergo a change. So what happens now? There are quantum systems, there are qubits which are not going to change. So for example, at the bottom end, let's say I still have a quantum state 0, but the top end, let's say I have a quantum state T1. Okay, right? So I will write new quantum state as a superposition of old quantum state plus, okay, let me write as a sin 1 and sin naught. That is easier. Psi 1 and psi 2. Or you can say psi naught and, okay, let me write down psi naught and psi 1. Okay. So this is a linear combination of both the old states and the new states. May happen where C0 and C1 are complex by nature. Remember. Okay. So fine. To some extent, I know what is the change. Now I want to read the system. Okay. I want to detect the signal. How do I detect the signal? Okay. Next process is, okay, detecting the signal or getting to know about the signal from analyzing the psi of t. Okay, so that we will do in the next half. Let's take a quick 5 minutes break and then we'll come back. Okay. Okay, I think we can start. Okay, somebody was asking where we can get notes in the canvas. We can get under the files. Okay, right. Okay, so let's get back how to make out the signal strength, signal information from analyzing the quantum state. Okay, the final quantum state after it gone under change. Okay, right. So this is called a readout process. Before going there, I have to bring in few things for you. Okay, so when I say like few little information about the basics required. Okay, let's see those what is required. When I say a quantum state is there like this, which means it is defined on a computational basis, which is 0 kit and 1 kit. Okay, whether whether it is, see here usually I have written like this, but somebody gives you a qubit, whether it is defined on this computational basis or there is other basis also. There is another basis. What is that? Which is plus ket and minus ket. Basically, what I want to have two elements of the basis perpendicular to each other and their length is orthogonal. Okay, right? So plus ket is 0 plus 1 divided by square root of 2 minus ket is 0 minus 1 divided by square root of 2. Okay, that is what plus kit and minus kit mean. Um, okay, now, so the quantum system is defined on the computational basis or any other basis. We can check using something called something called projection measurements. They would tell whether the system is in 0 and 1 or plus or 1 basis. Okay, so to know that, I need to have projection operators. So the projection operators are actually constructed from the basis elements itself. How? So I'll have a projection operator M. Let me call it as a M0. Okay, which is outer product of 0 with the 0. What is this one? This one is, okay, this one is a kit 0 and pre 0, which is 1000. Similarly, projection operator 1 is 1 1, which is 01 01 0001. So this is a projection operator. Now the question is whether quantum system is having alpha 0 beta 1 or not. I should make a measurement to find the psi nature. What we do, we will take m naught, act on the quantum state. Okay, what you will get, m naught, act on the quantum state. Let's say what I'll have, I have 0 0 acting on alpha 0 plus beta 1. So which is like this, you keep on the left, I'll have 0 alpha 0 plus 0 beta 1. Okay, as we know, alpha is a number, beta is a number. I can bring it out. Alpha 0, sorry, I'll have 0 inner product with the 0 plus beta 0 inner product with 1. So what I'll get, this 0 inner product 0 is 1, 0 inner product with 1 is 0. So I'll have 0 alpha multiplied by 1, which is alpha into 0. So I am getting a quantum state multiplied by some amplitude. Now to get to exactly what amplitude I have, what should I do? Even I should multiply on the left side also with a quantum state on the measurement operator. Okay, so if you do this time, what is the left side? Left side is 0 Bray alpha star 1 Bray beta star multiplying onto alpha 0. Okay, so now if you multiply explicitly, this is going here, this is going here, alpha star alpha beta star alpha. Okay, now as you can see, these two are numbers. Alpha star and alpha is absolute alpha square, 0 with a 0 inner product, beta star alpha, some number, complex number, 1 inner product with 0. By the way, inner product with 1 is 0. So what I left with, 0 inner product with 0 is 1. I'll have observation of the measure projection of quantum state. Okay, quantum state with the m naught is giving me alpha square. So I got the probability, conclusive results of probability of alpha square. Similarly, if you check m1, you would get beta absolute square. Okay, so this is how I'll get to know using the projection operators whether the system is in 0 or 1. Okay, right? Similarly, you can have a projection operators for plus ket and minus ket. By the way, these two are what? These two are the x basis elements, and the 0 and 1 are 0 and 1. You see, this 0 and 1, this is a z basis, z gate basis. Why I'm calling x basis and z basis? Because you add x on plus gate, you get plus gate only. You add x on minus gate, you get a minus of minus gate. Okay, you can cross check actually. Why? Because x act on 0 gives 1. Okay, and if you add x on 0 minus 1 divided by square root of 2, what I'll get? I'll get 0. Sorry, what I will get is 1 minus 0 divided by square root of 2, which is minus of 0, 1 divided by square root of 2, which is minus of minus ket. Okay, so for a x basis, measurement operators are plus ket. I'll write a subscript x now, which is plus outer plus. And similarly, for minus, projection operator is outer 1 ket outer 1. Sorry, minus ket outer minus ket. Okay, so these are the projection operators for the x basis, and so far I have not used a subscript z here. Let me write down z here. Okay, so this is how I'll know a quantum system is whether it is evolved to new form or existing in the old form. It has to exist either 0 or 1 or a plus ket or a minus ket. Only the probability amplitudes are going to change, right? So we will take that information or that idea, and we will try to analyze the quantum output state. Okay, so earlier we started, okay, the protocol, if you recall, we started with the quantum zero state, put that to a superposition state by acting what? By acting, okay, by acting a unitary operator on zero, I am getting a superposition state, or you can say initial state, which undergoing a change of unitary operator h psi of 0, I am going to get psi of t. Okay, now if you carefully see, there is a initial unitary operator which is in my control. There is a unitary operator h which is not completely in our control, only control part of the Hamiltonian we have in control. Okay, so now we need to understand what is psi of t looks like. What is this quantity? Now, as you can see, as we progress from 0 to psi of t, psi of 0, okay, let me cleanly write that part. Psi of 0, okay. 1 minute. Okay. Yes. Okay. Now, we will take, see, as you can see, the u of a, okay, u of a pushes the system from 0 to psi of 0. Okay, right? Now I have a psi of t. Okay, is there any way I can push that? Okay, I can push that to the states push this or convert this into the basis of 0 and 1. Okay. So we need to convert this into the basis of 0 and 1. It is simply like taking a projection onto 0, 1 basis. Okay. The nature of the system would remain the same. Only the projection is that from the position we will make out the information. Now, as you can see here, U of A is doing from computational basis to some other basis. Now, I can come up with some unitary operator P, which is doing a job of reversing the effect, okay, from 0 and 1 to somewhere else U of A is doing, right? U of A is doing zero computational basis to some other basis. Okay, so we can have the reverse effect of U of A. So that would, what is that will do? That is ensures psi of t going back to 0 and 1 basis. Okay, right? What I'm saying is I'm going to get a new coherent state. Let me write down new coherent state alpha ket. Remember, look, don't be confused with this alpha with probability amplitude. This alpha just I will write for a coherent state, which is equal to some unitary B acting on the final sensor state. Okay, so what it means, this is going to give me some C naught prime 0 ket, C1 prime 1 ket. Why am I using prime? Earlier, C0 and C0, C1 were already being used. See here, the C0 and C1 are already used. So I'll have some other new constants, which is C0 prime and C1 prime. Okay. Now, from the alpha ket state, from the coherent state, how much zero nature is existing, we have to find. Okay, how do you find? As you know, let's take inner product with 0 itself. It's like taking a projection. Okay, and then if you take a absolute square, that is going to give me what is the probability amplitude of system existing in the 0 state. Okay, so how did I get this idea? I just got it from the projection technique. Okay, see the projection technique, right? So now inner product with the 0 gives me the chance of system existing in the 0 state. Inner product of 1 with the coherent state with absolute square gives me, okay, gives me the chance of system exist in 1 ket state. So chance of system existing 0 ket state is taken from the top and 1 ket state taken from the bottom. Okay, right? Now, having known that, okay, we can make out some information. Now, the problem is this is all statistics. Means with one experimental result, I can't conclude. So let's say there is a probability 0 here, there is a probability 1 here. Why? Because we need to perform the experiment several times. Let's say if we perform this experiment n times, out of which we will get let's say n0 times, okay, 0 gate state, n1 times 1 gate state, which means p of 0 is n naught by n, p of 1 probability is n1 by n. Okay, so the probability is going to play a very very important role here. I will have two probabilities. Remember, p1 plus p naught is actually 1. Okay, right? So if I have to put that entire thing into kind of a flow chart, so the flow chart would be, okay, now, okay, the flow chart would be initialize the system into 0, first stage, okay, get the superposition, okay, by acting unitary on 0, okay. And the next stage is get the new quantum state of the system when system interacts with the Hamiltonian induced quantum interaction. Okay, right? After that, what we'll do, we'll get the coherent state from where? From taking so unitary operator B, which is z, just exactly opposite to u of a or dagger. Okay, now in the next stage we will find p naught from 0 alpha square, p1 from z1 alpha absolute square. Okay, now as you can remember, you can calculate only p naught, and p1 is simply equal to 1 minus 0 alpha square. Okay, right? So the next stage is calibration. Calibration is knowing the p of k, we need to get what is the signal strength. Okay, right? Okay, so that's the mathematics is slightly too much, I think somebody was saying. Okay, right? So what I'm saying here is the atom or the system in the ground state, I make it to superposition, and then interact with the signal. The signal interaction would change the amplitudes, and the change in the amplitude we are actually recognizing from the probabilities. Okay, so very simple. That is what the flow chart is actually saying here. Okay, now some physical examples we can check right now. Okay, wait a minute. Yeah, physical examples we'll check right now. So there is something called Ramsey measurement. Okay, Ramsey measurement. So it's a quantum sensing protocol. Okay, so which senses the parallel signal. So V parallel its points means the effect of quantum state being stretched or compressed so that the energy separation got changed. So this effect is actually V parallel effect. Okay, we want to find that effect. So basically the like oscillations were done between very close orbits, and later on oscillation is done with the far orbits. That may be the effect. Okay, so that is a Ramsey measurement, or also it's called Ramsey interferometry. So here step one is prepare the system in a zero state, state zero preparation. Okay, carefully see, you will understand with this mathematical example. Number two is convert that into a superposition state. What is the superposition state is? You take a Hadamard gate, act on this, you are going to get a plus gate state, which is 0 plus 1 divided by square root of 2 equals superposition state. So I will say my psi naught, or you can say, okay, my psi naught quantum state is 0 plus 1 divided by square root of 2, which is a plus gate state. Remember, it is still in computational basis 0 and 1. So only in short form I written as a plus gate state. Okay. Now the third step, interaction with the signal. So the interaction with the signal, first the system Hamiltonian is there. What is the system Hamiltonian? System Hamiltonian is E0, 0, E1. Let's say the system Hamiltonian is in such a way, the ground state energy of the system is 0, excited state energy is some H naught, H cross omega naught. What I mean is, the ground state energy is 0, excited state energy is H omega naught. So that is what I mean. So in that case, if you try to find what is the unitary matrix of UH naught would be exponential minus I H naught T by H cross. Exponential of a matrix. Okay. So since it's a diagonal matrix with only single element, it is straightforward. You can just say exponential of 0, exponential of minus I H cut omega naught T by H cut. H cut cancels. U of H naught of T, okay, is equal to 1, 0, 0 exponential minus H my I omega naught into T. Okay, right? So this is the unitary matrix which is going to put the quantum state. This unitary matrix put the quantum state into new quantum state like this. Okay, what is this? This is 1, 0, 0 exponential minus I omega naught T. Okay. Okay. So yeah. And by the way, right? So if you see this, if you see carefully this one, okay, so I can make out this is literally, okay, 1 by square root of 2, 1, 0 plus exponential minus I omega naught T 0, 1. Okay. Why did I write this way? Because psi naught we know already. Where is this? The psi naught. This one. Plus get state, right? So from there, you can make out, what would be the psi of t. What would be the psi of t? Okay. Fine. Now, let's say now I have Hamiltonian is also going to change with the environment Hamiltonian. So in place of H naught, I have to add HV also. The moment you add HV, okay, what happens is, if you can carefully see, okay, Hadamard acting on 0, okay, this time Hadamard acting. So this H, calligraphic H, regular Hadamard H are different. Hadamard acting on 0 gives a superposition. Okay, right? So literally adding a new HV is like a Hadamard. So adding new HV is like a Hadamard because a new quantum state undergoing a coherent state is actually done by pi by 2 pulse. Okay, what is pi by 2 pulse? Pi by 2 is a Hadamard action. Okay, so that means when I have a new signal quantum state is there, I act a Hadamard gate on that. By the way, what is signal state? Signal state I have here. Okay, so which is Hadamard acting on 1 by square root of 2 0 ket plus minus I omega naught t 1 ket. Okay, so if you carefully do, Hadamard going to act on 0. Just a minute, I'll keep it silent mode. Okay, Hadamard acting on 0 gives me a superposition. Hadamard acting on 1 gives me 1 ket 0 minus 1 ket divided by square root of 2. Okay, now there is 1 by square root of 2 inside is also is there. What I will do, I'll take it out, I'll get 1 by 2 0 plus 1 ket. Okay, exponential I omega naught t 0 minus 1 ket divided by square root of, sorry, no square root of 2. Okay, now let's rearrange this for our convenience, which is half into 0 ket. If you take common, I'll have 1 plus exponential I omega naught t. 1 ket if I just take common, 0 1 minus exponential I omega naught t I'll get. Okay, this is what I'll have, right? So now this is the new coherent state for me. Now I want to know what is the probability of system is in 1. We just saw earlier, which is equal to 0 alpha. This is the probability. Okay, so now I know what is alpha state. I need to take an inner product between 0 and alpha, which is like inner product of 0 plus minus I omega t. Okay, plus 0 with the 1 plus 1 minus I omega t. Okay, as you know, this is 0. Okay, what is the contribution comes from here? This is 1, so which is half into 1 plus minus I omega naught t. Okay, so now if I just take absolute square of this quantity, which is 1 by 4 1 plus exponential I omega naught t whole square, or absolute square. Okay, now to find absolute square, what you can do, let's take a common minus I omega naught t by 2. Let's take a common, so I'll have exponential plus I omega naught t by 2 plus exponential minus omega naught t by 2 whole square. Okay, why did I do this? Because, okay, this is a quantity. I can convert this into a simple sine and cosine terms. Okay, right? So let me put that. Take this outside the exponential, outside the square. I'll have exponential minus I omega naught t Whole square means by 2. Oh, there is a by 2, 2 cancels. I'll have this 4. Okay, right? And the absolute square of this. Okay, so exponential I omega naught t by 2 plus exponential minus I omega t by 2 whole square. So exponential minus I theta absolute value is 1. So this value I can simply ignore, and exponential I theta plus exponential minus I theta converted into what? It's a cos function. So which is going to happen to be a simple cos function. So I will have uh, okay, so 2 cos, okay, omega naught t by 2 whole square. Okay, so if I implement the square, I'll have 4 by 4 cos square omega naught t by 2. Okay, 4 cancels, there is a cos square, right? So I will get what is this quantity. Okay, p1 is 1 minus this quantity. So 1 minus cos square omega naught t by 2. Okay. Now 1 minus cos square is a sine square. Okay. Right. So with this, we will get what is a P1. Knowing P1, you can get you can get what is the signal strength. Okay. Fine. So this is how people find out the signal strength. How they do it is they are going to plot P1 versus time. Okay, versus time. P1 versus time they will plot. So they'll find what is the angular frequency. The angular frequency known, you can get P1. So angular frequency of the signal is actually telling the what is the signal strength. Okay, right? So the omega naught is the information we will capture or we will find through the probability. Okay, right? So this is a one example. How do we use a sensor, a qubit, to sense the external frequency? Okay, so here earlier there is some frequencies there. Let's say h omega. Later we'll find h omega. Okay, or initially let's say h omega naught is there, later we'll find h omega 1. Okay, right? So okay, it's called a Ramsey experiment or Ramsey interferometer or interferometry. Okay, so there is next one is called a Rabi measurement. Okay, so what I will do, I'll just we have how much time we have? We have 10 to 12 minutes. So let me use my lecture notes. Okay. Okay. So there is, let me see the questions. Superposition state can be achieved by applying Hadamard gate, right? Yes, of course. Here, the unitary operator is a Hadamard gate. The quantum circuit, am I right, sir? Please clarify if I am wrong. Okay. So remember one thing. Okay. So the Hadamard gate H, regular H, puts the quantum zero state into superposition. Okay, what is this is electron being super doing a oscillation between ground and excited. That is a superposition. Okay, now going from zero to this plus state is actually some unitary operator. Okay, so that unitary operator carries the information of the Hamiltonian. Okay, right? The H Hamiltonian. So the H Hamiltonian means the system and the surrounding Hamiltonian Okay, right? So that system Hamiltonian creates the Hadamard action. Okay, which means here H I am writing now, which is actually a unitary operator. So U of A is actually Hadamard gate, which is 1 by square root of 2, 1, 1, 1 minus 1. Okay, so the unitary operator is the Hadamard gate. Okay, and there will be a Hamiltonian corresponding to this Hadamard gate. That Hamiltonian is this top one. Okay, what you are saying is superposition state created by or achieved by Hadamard gate. Yes, you are perfect there. And here the unitary operator is the Hadamard gate. Yes, you are perfect there also. In quantum circuit, yes, in the quantum circuits. Okay, so for every operation, for every gate, there is a Hamiltonian associated with that. Okay, so just like I am saying, for the Hadamard gate, for the gate, okay, right, for the Hadamard gate, there is a Hamiltonian of Hadamard gate. For the X gate, Hamiltonian. For the X gate, there is a Hamiltonian of hex gate operation. There is a Y gate, there is a Hamiltonian of Y gate. There is a Z gate, there is a Hamiltonian of Z gate. How do we find? We can find the, as we know, H operation, this has to be unitary of minus IH T by H cross. Okay. Knowing the Hadamard or matrix U, you can just, what you can do, you can just take a log on both sides. Log on both sides, if you take this entire expression, what you will get? You will get minus I H T by H cut is equal to log of Hadamard. Okay, what is the Hamiltonian? Hamiltonian is, okay, IH cross log Hadamard divided by time. Okay, so this is the Hamiltonian. Similarly, for this is a Hadamard Hamiltonian, X gate Hamiltonian would be IH cross log of X gate divided by T. Okay, and Hadamard for Y gate is IH cross log of Y gate divided by T. Okay, right? So the gates are not just random things, they're actually designed by some Hamiltonians. So how to find that Hamiltonian? Through the gates. If you know the gates, you can get the Hamiltonian. If you know the Hamiltonian, you can derive a gate. Okay, so there is one more question. I think Padmavati ji is asking, what if the ground state energy 0 is a non-zero quantity? Yeah, so I think what you referred there, I think I understand the question. Yeah, here. Okay, so the ground state energy, which I am taking 0. Why I am taking is 0? Because with respect to that, I am measuring everything. So my reference point I am considering 0. From that point, I am counting. Okay, if that is not 0, means our calculations will be slightly tedious. Let's say we'll have omega naught, omega 1, two numbers we'll have. Okay, ultimately that is going to give me the same cos and sine, but the calculations becomes very tedious. That's why I just put that way. Okay, right, fine. Okay, so yeah, uh, yes. Okay, now since we have a very short time, what we'll do, we'll get into the hand notes. the lecture notes. That is much easier. Okay, wait a minute. Yeah. So we have completed up to, okay, this is finished. Okay, this is finished. Okay, Ramsey measurement, we just finished. Okay, right. So we will go to the something called a Rabi measurement. So the Rabi measurement is, okay, let's say I want to measure the perpendicular component or the signal perpendicular effect or transverse effect if I want to calculate. So what should I again start with zero state, initial zero, and then evolve the system into some superposition and involve the superposition to interact with the signal. What signal? The perpendicular signal, perpendicular part of the signal. Okay. So the perpendicular part of the signal may have sigma x and sigma y. So let's say it has only having sigma x part. Okay, we are not having the y part. We vx and vy na, vy part is not there. Let's say we assume for simplicity, in that case the signal Hamiltonian is simply h omega 1 sigma x. Okay, right? So where omega 1 is a Rabi frequency, let's say the signal is coming with the angular frequency of omega 1. In that case, this is what the Hamiltonian would look like. Okay, now knowing that Hamiltonian, you can create a unitary operator. Okay, so you create a unitary operator, you act that unitary operator on the initially prepared superposition state. Okay, now do the same calculations whatever we did earlier. Okay, now if you see, I want to, right, I want to have uh, yeah, right. Now I'll create a Hadamard action on the system to represent the interaction. Okay, when I do the Hadamard, system will go to 0 and 1 basis. Okay, 0 and 1 basis is like a coherent state. So the above what you see is a coherent state. To find the what is the chance of system is being in 0 and system is being in 1, we have to do the operation like the same exercise several times, statistics, and let's get the probability, which is going to get some sine square omega 1 t by 2. Okay, right? So where omega 1 is actually going to tell me about, what is the strength of perpendicular component of the signal. Okay, okay, fine. Okay, so yeah. Okay, so now the question is, how do we find exponential of a matrix? Okay, so for exponential of a matrix or a log of a matrix, if I want to find, for example, earlier I was showing this the like a log of x or exponential of y or anything. If I want to find, okay, if I want anything I want to find, I have to follow some strategy. What is the strategy is explained here. Let's say I want to find exponential of some sigma into some matrix. Okay, let's say here I have some H matrix, which is some I vector. Okay, 1 into I vector. Okay, that's like a x. I is a unit vector of x component. So in that case, how do I find? Is explained in detail. Okay, so I'm not going into the details. You can just check this part. Okay. Okay, fine. Now let's come to a specific case. How do we find exponential of a Hermitian matrix or our X matrix or a Y matrix or a Z matrix? So that is what is shown here. Okay. So again, this is a lot of mathematics. Just for your reference, I have added. Okay. So when it comes to small signals, we can capture all the Vx, Vy, and Vz, perpendicular and parallel all the components, and ensure that there is some effect on the system. What is that effect? From there, you can figure it out. Okay, so it's like ensemble of all the cases, parallel and perpendicular cases. We will take and we will find the effect of the system onto the rope. Okay. So there is some error analysis also discussed. We are not getting into the details. Probably this error analysis we will discuss as a part of the quantum sensing QT-07. Okay. So I'll stop at this point. Okay. It's 4:56. So if there is any questions, I'll just discuss. Otherwise, I'll just end up at this flow chart. This is sensing algorithm. Okay, so when it comes to mathematics, some mathematics is involved. Okay, so what I suggest you people do, please go through the submitted hand notes, this lecture notes. You will really understand everything. Okay, remember. So in the books, I think this detailed explanation is not there. They will write the shortcut. So just to ensure the explanation is understood, I have added here. Yeah, so Surendra ji was asking a good question. May I get all the spectral data by using quantum sensing? Yes, of course. Yes, you can get. So whatever I was showing here, you are getting only single frequency omega naught and omega 1, right? So it's not just that. So, okay, if the incoming signal, if there is an incoming signal, okay, so let's say it has omega 1, omega 2, omega 3, omega 4. Okay. So four signals are there. They're together, let's say they are going to create some pulse. Okay. This pulse comes and interacts with a very quiet qubit, which is minding its own business and oscillating as per its wish with some angular frequency, with Rabi frequency. When this pulse is having all omega 1, omega 2, omega 3, omega 4 angular frequencies, it comes and interacts with this one. What happens? It is supposed to have some alpha of t, beta of t at some given point. Because of this interaction, what happens? The alpha of t and beta of t gets changes to some alpha prime of t, beta prime of t. Okay, so this change is actually carries the information of omega 1, omega 2, omega 3, omega 4. Basically, there is a resultant angular frequency created. With that angular resultant frequency, this atom is going to oscillate. Okay, so from the resultant frequency, you can make out all the existing frequencies. Okay, so basically, you take the signal out from this particular sensor. Okay, that sensor is, let's say, having some signal output like this. Okay, all the four frequencies, let's say it has. Okay, omega 1, omega 2, omega 3, omega 4 it has. What I'll do, I just take the signal and take a Fourier transform of that, and then I'll get a peaks, okay, corresponding to omega 1, omega 2, omega 3, omega 4. In that way, we will get the input signal information. Okay, I hope I answered your question. I think Surendra ji, I guess. Yeah. Okay, fine. So this hand notes as well as the whatever running notes I have written today, and also my lecture notes is already uploaded to the canvas. You can just go through it. So Today we discussed how the control signal is mathematically written, how the overall Hamiltonian is going to create a new unitary operator. That new unitary operator, how it is going to induce change in the qubit operations, and how that changed qubit operations were measured using projection operators. So using projection operators, I can convert the quantum system into some coherent state. Knowing the coherent state probabilities P naught and P1, I can make out what is the input signals frequency, either omega 1, omega 2, or anything, just by taking a spectrum of that signal coming out from the probe. Okay, right? So, thank you very much for listening. We will see tomorrow the very basics of the materials, quantum materials. Okay.
Sir, Dr. Aswaji, thank you very much for your wonderful session. I think the AICT Academy, Sudhakarji and other people, they are busy with some Teachers' Day function there. So it's really a very useful session, sir, and very inspiring.
Thank you, sir. Thank you. Thank you.
I request today there are around 450 participants are there. I request others to join so that we can. We have set a target of 1,000 faculty members. Still miles to go. I request all the rest of the 500 faculty members to join and complete the assignments as well as quiz. Thank you very much once again, sir.
Yeah. So I'll upload both the hand notes to the canvas. Okay,
Yes.
but my notes is enough. If somebody wants to even refer to the hand notes, you can then refer it. Okay, see you tomorrow. Bye bye.
Thank you. Thanks.